how do you take a triangle wave and turn it into a nice sine wave like this? There's lots of ways of doing it, but how about a very simple minimum parts component way of doing that? I'm Professor Fiore, and I'm going to show you how. Time for the super simple sine shaper, a tongue twister and interesting circuit. So, what we're going to do is we are going to take a triangle wave and we are going to turn it into a nice sine wave. Not super wide frequency range, not super hi-fi ultimate tweak audio distortion, but a good serviceable sine wave that you might use for a variety of different projects and such. So the trick here is to exploit the true characteristic of a diode. What do I mean by the true characteristic? Well, typically when we think of diodes, we think of a simple kind of curve describing them that is not allowing current through at small voltages. And then when we hit a voltage up around 6 or 7/10 of a volt, the diode turns on and it allows current to flow. All right, it's a simple little model. It works pretty well. But remember, it's just a model. So here's the circuit I'm going to talk about. Triangle wave generator, resistor, pair of diodes over here, right? Configured in opposition. Now, normally you would look at something like this and say, wait a minute, this is just going to like clip a waveform to, 7/10 of a volt or thereabouts when these things turn on. Yeah, it's a decent approximation, if you're talking about, a 10 volt input or a 50 volt input or something like that. But we have a little triangle wave that's only 500 millivolts peak. It's only half a volt. So if you use that simple model where we say that, the diode turns on at around 6 or 7/10, well, at 5/10, it shouldn't be on. In other words, it should be an open according to that model. And if that's the case, if these are opens, then V out's going to look just like the triangle wave. But that's not really what's going on, right? Let's take a look. Here's your classic diode curve, right? It's flat down here. You're basically getting no current until we get up to this knee of somewhere around 6 or 7/10 of a volt, and then it takes off, all right? Now, the thing to remember is that the conductance of this device is found as the slope of the curve at some operating point. All right, how steep is it? If it's very steep, it's high conductance, meaning it's very small resistance. So this is small resistance, and back here, the slope is essentially 0. So we're looking at, huge resistance, right? No conductance. But if we plot this a little bit differently, in other words, instead of using a linear scale, if we go to a logarithmic current scale, right? So notice this is changing by decades. We see it's something entirely different, right? We see a straight line. Instead of this exponential takeoff, right? We see a nice constant line. So what this is telling us is, yeah, over here, this is a very low resistance, and back here is a very high resistance, but it's a consistent change through that range of voltages. We don't say open, right? Open down here and then basically short over here. It's not really what it is. So when I get back to this circuit, what we're saying is, look, when the triangle wave is very, very small, when it's 10 millivolts, 50 millivolts, maybe even 100 millivolts, the resistance of these diodes is very, very high, bigger than this R1 over here of 100K. So what we get out is what we put in. But in a very smooth, gradual sort of way, and by gradual I mean across this 500 millivolt peak, the resistance of these drops. And as it drops, we get less and less of the triangle wave to V out. So if you think of this triangle wave, right, nice straight sides, and it just keeps sort of dying off as the amplitude increases, well, we can approximate a sine wave, right? So instead of a straight line, we're going to get something that kind of comes up and just sort of dies off, all right? So what I've done here is I've just thrown in a 1 kilohertz triangle wave at 500 millivolts peak, half a volt, and I've also thrown in a sine wave at a somewhat smaller amplitude just so that we can compare the output voltage versus a true sine wave, right? I mean, the sine wave that's coming out of the simulator here is a pure sine wave, right? So we're just going to do a transient analysis on here. So I'm going to go from 0 to 2 milliseconds so we can see a couple of cycles of the input waveform, see what happens at the output. Okay, so let's get the legend out here. So first of all, the triangle wave is this sort of olive green color, right? Very obvious. But the sine and the V out, there's a green and a maroon, and they appear to be right on top of each other. I mean, just looking at this, we can see there's a little bit of variation right around the tips here, okay? But it actually looks pretty nice. And we can see that a little bit better if we separate our curves out. All right, so here's our V out. This is our sort of force fit sine wave. And here's the sine wave that we're using as a reference. And I've just scaled these so that they're the same size. And here's the triangle wave that we started with. Now, if you're wondering, hey, where'd the triangle wave come in? Well, there are many ways of generating high quality triangle waves. All right. And yes, you can generate sine waves with various kinds of oscillator circuits. I mean, you can go as far as making digital analog converter circuit with high resolution, many bits of resolution, and get a very, very, very high quality sine wave, right? Beyond your average hi-fi. Okay, super, super high, direct digital synthesis, super, super high quality sine wave, right? But, that's kind of complicated. Microprocessor and all of the associated gear associated with that. So this, on the other hand, come on, you got 3 components. You got a resistor and a couple of diodes. And this is actually looking pretty good. Well, yeah, visually it's looking pretty good, but I mean, is it really all that good? Well, a nice way to check that out is to do a distortion analysis. So in Tina, we're just going to call up Fourier analysis. And this is going to look at the first 16 harmonics. And I'm just going to calculate this out. And the number we come up with over here is 0.935%. So it's under 1% THD. That's not bad. Like I said, it's not, tweak hi-fi, but for general purpose work, it's not bad at all. Now, if you're thinking, well, okay, but, I only have, a few hundred, 300 or so millivolts out of this thing. What am I going to do with that? It's not big enough. Well, you can run it into a little op amp, for an amplifier out here and crank that signal up to several volts, 10 volts peak. Okay, that you can do. Another question we might ask, being this is just a simple passive circuit, is what kind of frequency range do we have? How high up does it go? How far down does it go? Lower limit on this thing, I mean, this works really great at crazy low frequencies. The upper limit, you'll start to see phase shifting and some other waveform distortions. I would say this is going to produce a decent waveform up to maybe 510 kilohertz. You just saw the 1 kilohertz. That's not too bad. If you try to get up to like 100 kilohertz or something like that, you're going to start seeing noticeable waveform distortion. And I will admit this circuit is a little tweaky. If you use different diodes, like for example, if you had some 4001 rectifying diodes kicking around, you're not going to get nearly as nice of a waveform. Another thing that will impact this is the precise value of the resistance. So you can kind of play with that a little bit. You might want to monkey with that for whatever your application is. There are some other sort of fancier little things we can do with here. But this by itself, I like it because it's just 3 components, and you can just sort of bend or force fit this nice triangle wave into a halfway decent sine wave. But let's go in and just try some different frequencies, all right, just so you can see. So let's go from 1K. I'm going to bring this down to like 10 hertz. So, I mean, let's just drop the darn thing, right? And what I'm going to do is I'm also going to change my reference sine wave so it'll be easier to compare them. Alrighty. Now let's go and do the transient analysis. And of course, I'm going to have to change the cycles on here. So let's go from 0 up to 200 milliseconds. And look at that. Wow, that is nice, isn't it? I mean, here's the original at 1 kilohertz. It's almost the same thing, right? So, you know, the distortion, the clarity of this waveform, you could just keep pushing this thing lower and lower and lower. We start going higher, and we will see some distortion. All right, so like I said, you can get a decent result up around 510 kilohertz. So let's just make this 10 kilohertz. So we are going to start seeing some shifts, phase shifting, and so forth. Change our sine wave as well. And let's do the analysis. Transient. And once again, we're going to have to change this. Let's make it 0.2 mils. There you go, right? So you can, in fact, see a little shifting right here, right? Notice how this has come off a little bit. Let me go back to the 1 kilohertz, right? That lines up really nice here, okay? But at 10 kilohertz, now the tip is looking pretty good, but these sides, so this isn't too bad. I mean, it's really just delaying the waveform just a little bit. It's still a pretty nice sine wave. You start to really push this. You get up to like 100 kilohertz, you're going to start seeing some noticeable waveform distortion. Sinusoidal will be more of a suggestion than a reality. Okay? Very good. So, did you think you could get that kind of performance out of just 3 passive components? You can, right? Just remember, we're talking about models. You think of this as just sort of a 2-step model? Yeah, not really. It is continuous resistance change. And bearing that in mind, we wind up with this circuit being quite successful. All right. I'll see you next time. Take care.